Buckle up, listeners, because today we are taking a deep dive into a theory that makes even Einstein's ideas seem almost, well, normal. We're going deep into the mysteries of gravity, but on a scale so large it boggles the mind. And we have a new paper as our guide. Scalar radiation with a quartic Galileon.
That's a mouthful, isn't it? But believe me, the concepts in this paper are utterly fascinating.
So, before we get lost in the weeds of theoretical physics, let me give you an analogy. Imagine trying to figure out how a car engine works, but all you have to go on are the exhaust fumes. That's kind of what it's like trying to study gravity sometimes. We have general relativity, a brilliant model that works wonders for explaining gravity in our little corner of the universe, our solar system. But when we try to stretch it to encompass the entire universe, well, things get a bit, shall we say, less clear.
That's a great analogy. General relativity, or GR, as we physicists like to call it, is incredibly accurate, but only up to a point. When we start looking at huge structures, like clusters of galaxies or even the expansion of the universe itself, we start to see some gaps in our understanding. We need something more, something to supplement GR. And that is where these modified gravity theories, like the Galileon we're discussing, come into play.
So are we talking about a sort of gravity plus then? And this particular paper focuses on a specific type of Galileon, one with a quartic interaction. What does that even mean?
You're spot on. This quartic interaction basically means that this version of the Galilean theory is more complex, more powerful. It's a bit like comparing a regular car engine to a high-performance one. They both make the car move, but the way they work is subtly, but importantly, different. And what makes this paper even more exciting is that it's the first time anyone has actually simulated this specific type of Galilean in action.
Wow, okay. I can tell already that this is going to be a wild ride. But before we get too far ahead, you mentioned something called the Vainshtein mechanism. It makes me think of a chameleon, changing its appearance to blend in.
Ah, yes, the chameleon effect. It's a fantastic way to visualize how these modified gravity theories can exist without contradicting everything we already know about gravity here on Earth and in our solar system. You see, this Vainshtein mechanism allows the effects of the Galilean field to essentially hide near massive objects.
Wait, hold on. Gravity can play hide and seek. You've got to tell me more about this.
It's more like cosmic camouflage, really. Picture the Galilean field as a chameleon moving through space. When it gets close to a massive object, like a star or planet, it blends in, effectively becoming indistinguishable from what general relativity would predict. But as you move further away from those massive objects, out into the vast emptiness of space, the Galilean's true influence starts to reveal itself, and it changes how gravity behaves over those vast cosmic distances.
Okay, so we have this powerful chameleon-like Galilean theory. But if it's so good at hiding, how on earth can we even study it? It's almost like trying to study a ghost, isn't it? Earlier you mentioned simulations. Is that how we do it?
That's right. If we can't directly observe this Galilean in action, we can at least try to simulate its effects using incredibly powerful computers. We're basically creating miniature versions of the universe inside these machines.
Mini universes. Whoa. So what exactly are these simulations showing us? What are we creating in these computers?
This is where things get really interesting. The study we're looking at today focused on simulating what's called a binary star system. So imagine two stars, each one much more massive than our own sun, locked in orbit around each other, spinning wildly.
Okay, yeah, I can picture that. Two stars doing a sort of cosmic dance. And
Yeah.
with all that swirling mass, I bet the gravity in that system would be intense.
Exactly. And remember, this Galilean field is changing how gravity works, especially in these more extreme environments. By simulating a system like this, the researchers could observe how the Galilean field would behave, and most importantly, what kind of radiation it would produce.
Wait, radiation? Are we talking about, dangerous radiation, the glow-in-the-dark kind?
No, no, not that kind of radiation. Nothing dangerous. This is more fundamental. It's just how energy and information move through the universe, even across the vast distances of space. Think of it like ripples spreading out from a stone dropped in a pond. Those ripples carry energy, and they tell you something about the object that created them.
Okay, that makes sense. So you're saying this Galilean field creates its own ripples, its own radiation, as these stars go about their cosmic dance.
That's it. And by studying these these waves of energy, we can learn about what created them. In this case, our hidden Galilean field.
This is so cool. What kind of ripples or radiation, I guess, did they observe? Was there anything unusual about it?
This is where the findings get really fascinating. The main type of radiation they observed is called quadrupole radiation. Now, what's really interesting is that this quadrupole radiation is also predicted by general relativity, when you have accelerating massive objects like we do in this simulation.
So both good old general relativity and this new powerful Galilean theory both agree that these dancing stars should be giving off quadrupole radiation.
They do,
Yeah.
but, and this is a big, but the specific pattern of this quadrupole radiation that the quartic Galilean predicts is different. Different from what we would expect to see from general relativity or from simpler models.
Well, hold on. You're saying this quartic Galilean thing leaves a different fingerprint in the radiation? That's amazing. Like finding a message in a bottle from another dimension or something. Tell me more. So we're not just talking about some random ripples here. We're talking about a specific, identifiable pattern that could only come from this quartic Galilean, like it's got its own signature.
The cosmic fingerprint, exactly. And just like a fingerprint can be used to identify a person, this unique radiation pattern could help us confirm if this specific type of Galilean is out there influencing the universe.
It's like we could look out into space and say, yep, that's our quartic Galilean up to its old tricks. But running these simulations, deciphering all that data, I can't imagine it was a walk in the park.
Oh, you're absolutely right. Even with our most powerful computers, simulating these complex gravitational interactions is incredibly difficult. To give you an idea, I want to read a quote from the paper. What makes the quartic Galilean particularly challenging is that analytic attempts to describe scalar radiation fail. Basically, our everyday mathematical tools just weren't enough to solve this problem. We needed the brute force of these simulations to make any headway.
So we needed to throw the entire world's computing power at the problem just to begin to understand it. Pretty impressive. But let's zoom out for a second. What does this all mean for us, for people who don't spend their days simulating mini-universes?
It goes back to your car engine analogy. We're starting to get glimpses of the engine under the hood of gravity, the mechanisms driving it in the largest scales. And these hints, even though they require incredibly powerful tools to detect, could change everything. Imagine listening for a whisper in a hurricane. That's what we're doing here.
We're listening to the whispers of the universe. I love that. But how do we hear these whispers? Where do we look for evidence of this Galilean radiation out there in the vastness of space?
You remember those pulsars we've talked about? The rapidly spinning neutron stars that act like cosmic lighthouses, emitting incredibly precise pulses of radiation?
Oh yeah, those incredibly dense, crazy fast-spinning remnants of dead stars. Aren't those the things that spin like 1,000,000 times a second or something like that?
They are. And as it turns out, they might just hold the key to solving this puzzle. You see, if we observe these pulsars in binary systems, the way their pulses vary, those tiny changes in their timing could be affected by the type of scalar radiation we've been discussing.
So by studying the blinking patterns of these cosmic lighthouses, we might be able to detect the faint signals of the Galilean at work.
Unbelievable. It's like using the entire universe as our own physics laboratory.
Exactly. Of course, we still have a lot to learn. We've just scratched the surface here. There's a whole universe of modified gravity theories out there waiting to be explored.
That's the beauty of science, isn't it? Every answer leads to more questions. So to all our listeners out there, if you're as fascinated by the mysteries of gravity as we are, keep your eyes on the skies and your ears open. This is just the beginning of a very exciting journey.